Hello, this is a quick walkthrough of Exam 1 from spring 2017 for Calc 3. Okay, question 1. Let L be the line that's parallel to these two planes and also passes through this point. At what point does it intersect the plane z equals 0? So as always with these questions, it kind of helps to draw out what we're dealing with. We're looking at, well, it helps if you can draw well, which I cannot, but we're dealing with the intersection of two planes. Hopefully you can kind of see that there will be some line that passes through this intersection point of these two planes and only one line with that slope. But what they're saying is we want the line parallel to this line that passes through some other point. And so how can we go about finding this? Well, oh wait, I kind of want that drawing back if we get rid of this though. Well, if we see the normal vector, let's call this plane A and this plane B. The normal vector of plane A will be going like that. The normal vector of plane B will be going like that. We can take the cross product of the normal vectors of A and B to get the slope of the line of intersection. And so let's just do that. We know that we can pull the normal vectors out of these two planes by looking at the coefficients. So we're taking the cross product of 1, -1, 1 with 2, 1, 1. And then we're just going to adjust it so that we make sure it passes through this point. So this cross product is going to give us, let's see, -2, -3. Wait a second. Sorry, it's been I think 2 months since I took a cross product. No, more like 1 month. This is right after fall break, not fall break, winter break that I'm doing this. I'm sitting in my dorm room the day before classes start. Let's see, can I do a cross product? Yes, 1. There we go, and then 3. Okay, so there's our cross product, and we know that if we're parametrizing this line, and let's say we parameterize it with respect to time. So for every unit t, we want to move -2, 1, 3. But we also need to make sure that when t is equal to 0, is an easy way to do it, that we pass through 1, 3, -3. So here's our parameterization of our line. And then we need to find what point this line intersects the plane z equals 0. Well, we see that when t is equal to 1, our z component is going to be 3 minus 3. So there is our value of t. So t is equal to 1, and we see that this will give us the point -1, 4, 0. Let's suppose the trajectories of two particles are given by r1 of t and r2 of t. We're supposed to find the angle between their tangent vectors at the point of collision. So the tangent vector for each one of these is just going to be r prime of t. So r1 prime of t and r2 prime of t are just going to be the derivatives of each of these components with respect to t. So 1 and then 1 over root t and root 2. And then down here, 2, 2t, 2t minus 2. Okay, and we know that the angle theta in between these two vectors is going to be the inverse cosine of r prime 1 of t dotted with r prime 2 of t over the magnitude of r prime 1 of t times the magnitude of r prime 2 of t. Yeah, there we go. Okay, and that just comes from the definition of the cross product. You can solve for that on your own if you want. So now we just have to find all of this stuff. And it would also help us at this point to figure out what the point of collision, what t value for which these particles collide. So all we have to do for that is to see what t value satisfies, setting all of these components equal to each other. So let's start with the first component. T plus 1 needs to be equal to 2t. Well, that's just the same thing as saying t equals 1. And if we check our other components, we will see that our second component, those will match, because 2 times the square root of 1 is just 2, and that's equal to 1 squared plus 1. And then our third component will give us root 2. Yes, okay. So t is equal to 1 for our point of collision. And so we can go right in and replace some of these things. So r prime of 1, sorry, r1 prime at 1, that notation looks absolutely terrible. R prime of 1 at 1 is going to be 1, 1, root 2, whereas r prime of 2 at 1 is going to be 2, 2, 0. Okay, so now we can start replacing some things. Theta is going to be cosine of negative 1 of the dot product of these two, which will give us 4. And then we are going to divide by, well, the magnitude of each of these. The magnitude of this guy right here, 1, let's do, yeah, okay, is going to be 2, because we will get the square root of 1 plus 1 plus 2. So 2 times magnitude of this guy over here, which will be the square root of 8. So 2 root 2. So we can simplify this down to 1 over root 2, which is the same thing as root 2 over 2. And the inverse cosine of that is pi over 4. Whoops. Yes, we're good. Okay. Oh, that's interesting. I'm not really sure how I did that, but I skipped question 2. I did not mean to do that. Hopefully, if you're watching this in order, you didn't just get seriously confused there. That was completely my fault. Let's go do number 2. It's a really quick one. We're trying to identify what kind of quadratic surface this guy is, and we can remember that whenever we're trying to identify one of these surfaces, the only thing that matters is what terms are squared and what terms are positive and negative. It doesn't matter the coefficients. So we can get rid of this 4 and just turn this into a 1, and we will have the same thing going on. And we see that simplifies things a lot, because now this is in the exact equation for a hyperboloid of 2 sheets. And that's just by memorization. You kind of have to go and memorize those, because it's very helpful later on in the course. And it's just, I don't know, it makes your life a lot easier when dealing with those questions. Okay, we are told that a particle moves with acceleration of 0, 0, e to the t. Here we go. Just expanding that out, because they just give it to us with a k component. I like to look at things in this way, with initial velocity and position given by v of 0 is 0, 0, 0, and r of 0 is 0, 1, 1, respectively. And then we want to find where the particle is at t equals 2. It's important to note for later on in the course, I just started mentioning this in videos earlier today. I think it's good. A capital 0 means a vector with value 0. And so that in this case, that'll be 0, 0, 0, just like we wrote out there. But it's good when you get into surface integration and Stokes' theorem. That becomes a thing that you have to recognize because you'll be taking integrals. You'll be taking integrals of something ds with a vector symbol, and sometimes you'll take, oh, that's a really nice integral. That thing right there, it's one of my better, I like that one. Or you'll be taking integrals ds with an s capitalized, and those are actually the same thing, but at least my professor was not clear about that at all. And you know, that's a nice thing to know whenever you see capitalization like that. So let's do this. So we know that in order to get from acceleration to velocity and then to position, we need to integrate. So integrating a of t, we would get v of t as 0, 0, e to the t. And then we need to switch everything around so that we satisfy this initial value. When we plug in t equals 0, we're going to get 0, 0, 1. And so we need to subtract 1 here. And now we have what is our actual v of t. And then finally, r of t is going to be 0, 0, e to the t minus t. And we need to, again, make sure that we satisfy this guy right here. Our x term is good. Our y term, we need to add 1 to. And our z term, well, when we plug 0 in, we're going to get 1 again. And so we don't need to do anything to that. So finally, we're looking for the position of the particle at t equals 2. So r, not r of t, r of 2 is going to be 0, 1, e squared minus 2. Nope. There we go. Particle moves along, I don't like that wording. Particle moves along according to r of t is all that for t greater than or equal to 0. What is the x coordinate of the particle after it has traveled a distance of 2 units along the curve? And we know that we can find this by taking the integral from 0 to, let's say, a of r prime, of the magnitude of r prime of t dt, and we say that that is equal to 2. And then really this a value is the t value so let's drawing this should probably help. Let's say that we have our curve here. Really what we're finding is this a value is going to be the t value for which we have traveled 2 units to get to. And that wording is absolutely terrible. Hopefully you understand what's going on here. This is just an integral with respect to arc length. That's why you know an arc length is coming out of it. So we can find our r prime of t as 5, negative 3, 4. The magnitude of that is going to be 25 plus 9 plus 16, which will give us root 50, and root 50 is going to be root 50, yeah, 5 root 2. So in here we're just going to have 5 root 2, and okay, perfect. So getting rid of that, we see that this integral, all this is going to equal is 5 root 2 t evaluated on 0 and a, which is just 5 root 2 a minus 0. Or we can just say that 2 is equal to 5 root 2 a, or 2 over 5 root 2 is equal to a. Okay, we're almost there. So this is looking pretty ugly, and it's not looking like anything that we really have in our answer choices, although this is E is just this inverted. But things get easy when we realize we're looking for the x coordinate of the particle. All we have to do is plug that into x equals 5t, where t is equal to this guy. This 5 is going to cancel with this 5, and we will see that x is equal to 2 over root 2. If we multiply each side by root 2, we will get root 2. And there's our answer. Let's consider these limits and see which one of the following statements is true. Again, generally with these, it's a general rule that one of these usually does not exist and the other one does exist. And you almost always have to prove that the one that doesn't exist does not exist because of the two-path test. That's an easy way to go about it. And then usually the other one does exist because you can directly plug in and see that it doesn't equal 0 over 0, excuse me, or you'll be able to factor something to get to get an answer out of it. So let's look at what we're dealing with. Number 1 here. I don't know what's making that noise. I hope you can't hear that. Number 1 here, we can't really factor anything. And so we're going to go on the hunch that this one does not exist and try to apply the two-path test. So if we approach it on the line x equals 0, we are going to get, well, we're still going to get 0 over 0, which is what we get, I should have mentioned that earlier, if we directly plug in 0, 0 in. That should always be your first step because a lot of the time, or like half the time, it will actually evaluate to something. Now if we approach on the line x equals y, we will get, if we replace every x with a y, we will get y over root 2y squared, or root 2y, which is just going to give us 1 over root 2, or, come on, root 2 over 2. Sorry, I have trouble switching my pen around. There we go. So we see that by the two-path test, this limit does not exist, as it doesn't always approach the same thing coming from different paths in 3D space. So we're down to just C and D as options. And looking at number 2, it could be easy to plug in or to fail to plug in these guys directly and just try to go apply the two-path test. But we don't even have to, because if we plug in 0, 0, we're going to get 1 over 1 plus 1, or 1/2. Okay, a weird one that they don't really ask questions like this much anymore, and they've only asked this one, like a question like this once. So I wouldn't really worry about this if this is weird, but it's really not a weird question. We're trying to find the domain of this function. The only kind of connection that you have to make is that the natural log function is only defined, so ln of x only works for x greater than 0. And that's important. So keeping this thing above 0, let's see, what can we do? Well, if x is greater than 0, then y has to be greater than -2. Because if it's -2 or less, we are going to have a negative argument in there. Okay, so that's one condition for us. But then we also, we also know that x can be, and really I should use a different variable a. There we go. If x is less than 0, y just has to be less than -2, and so that we'll have a negative term on the bottom and a negative term on the top. And we see that that is answer choice B. Yep, okay. Number 8, we have z, which is a function of x and y, where fx is this guy, fy is this guy, x is a function of s and t, and y is a function of s and t, and we're finding zt. So this is just multivariable chain rule question, where z of t is going to be fx xt plus fy yt. Okay, so we know that s is equal to 2, t is equal to 1, so that will allow us to figure out what x and y are equal to, because x is equal to, in this case, 2 plus 2, so x is equal to 4, and y is 1. And so that lets us start filling in some of these blanks, because fx is just expressed in terms of x and y, where this guy is going to be equal to 4 if x is 4 and y is 1, and fy is 1 plus 16, so 17. So we can replace these guys. Okay, perfect. And the only thing we have left to do is to find xt and yt and evaluate those guys at our values for s and t that were given right there. So xt will give us 2, yt will give us 2t, where 2t is 2. Okay. So we can replace our xt with a 2, and we can replace our yt with a 2, and so our answer is 42. Perfect. If f of x and y is equal to this whole thing, let's find the mixed partial derivative of that. And remember, we can do fxy, or we can also do fyx, and we should get exactly the same thing. But in this case, I think we're going to do fxy. They don't generally try to trick you with that. It's usually exactly the same amount of work to do it either way. You just do more work in a different part of the question. So let's find fx first, and then we're going to find fxy. So fx is going to be 1 over xy squared plus x multiplied by 1 plus y squared. And fxy, well, we have a y on the top and the bottom, so we are going to need to apply, still don't know if that wording was correct, but you know what I mean. We're going to apply the quotient rule. So this will give us big quotient with xy squared plus x squared on the bottom, and 2y xy squared plus x minus 1 plus y squared times 2xy on the top. And let's see, it seems like they think we can simplify this guy down. I really hope we can, but it looks like our denominators work. Every single one of these, besides 0, at least, has the same. Well, actually, 0 does have this denominator. This 0, we can just see this as 0 over xy squared plus x squared. But that's a little, that doesn't particularly matter. So let's take this numerator out and look at what it expands to. This will be 2xy cubed plus 2yx minus 2xy minus 2xy cubed. Okay, and in fact, this is true because these guys are going to cancel, this will cancel, and we will be left with 0 over all of that. So let's make sure that 9 is A, which it is. Okay, if z is equal to this thing, then the tangent plane to the graph at u equals 2 and v equals 1 is what? So we can express this tangent plane, because we're explicitly defined in the form of z equals something, as z minus z naught equals zu u minus u naught plus zv v minus v naught, where u naught and v naught are just these guys over here, and we can go in right away and replace those. And really all we need to find is zu and zv and evaluate these guys at 2, 1. Zu is just going to be negative 9 over u plus v squared squared. And ZV is going to be negative 18V over U plus V squared squared. And evaluating these guys, we see that our denominators in both cases will be 2. Okay, so 3, so 9. So this whole thing is going to evaluate to negative 1. And over here, this guy will evaluate to negative 2. And so we can replace these in here. And also our Z naught, we're just going to get from plugging 2 and 1 into this equation here to find what Z value what Z value we're kind of sitting at right now. So this is going to be 9 over 2 plus 1. So Z naught is 3. And theoretically, this is equal to one of our answer choices up here, but we kind of have to expand things out and move things around to see what we're actually dealing with. So we're going to have Z minus 3 equals negative U plus 2 minus 2V plus 2, or Z plus U plus 2V equals 7, which is answer choice D. Let's suppose that the graph of Z equals G of X and Y intersects the plane X equals 0 along this curve, and we're looking for the partial derivative of G with respect to Y at 0, 2. So the only thing you have to recognize here is that this kind of level curve for X equals 0 is really just kind of a snapshot of what the overall function is doing at that specific value for X. And I know that picture means absolutely nothing to you. It means nothing to me too, but it distracted me for a sec, so that was good. So all we're going to need to do to find GY is to take ZY for this curve, which is just going to be 3y squared plus 4y. And we see that Y, we're plugging in 2 for that, so ZY at 2, really I shouldn't notate it that way. ZY is going to be 12 plus 8 or 20, and that is our answer. This is an extremely simple question asked in a little bit of a weird way. Okay, question 12, we have an implicit differentiation question where we're looking for ZY, and we know that we can say that ZY, that's just the same thing as partial Z, partial Y. And our equation for that is negative D dy over D dz. So let's find these guys. D dy is just going to be negative 3y squared, whereas D dz is going to give us 2z minus 1. And we can evaluate these guys easily because we know our x, y, and z values. Here we're going to get negative 3, and here we are going to get 3. And so negative 3 over 3 is just going to give us 1. And there's our answer. And we're done. This is a relatively quick and painless test compared to a lot of the other ones. And if I could go back now, this is the one I would recommend to start your practicing with.